Good evening, everyone. So, welcome to my YouTube channel, Math Podcast. So, today we are going to see fourth lecture on direct product. In this lecture, we will study internal direct product of two groups. Okay? Internal direct product of two groups. So, what is the definition of internal direct product? Internal direct product. Let's suppose H and K are subgroups of a group G of a group G, then we say that G is an internal direct product of H and K if H and K if first every element of H commutes with every element of K. Okay. Second one, every element of G is uniquely expressible expression as a product of of an element of H by an element of K. Okay. So we have two properties. Every element of H connotes with every element of capital K, and every element of G is uniquely expressible as a product of an element of H by an element of K. Okay. So this is the definition of internal direct product. Okay. So we'll do one result on this. So let's see its theorem. Suppose a group B is an internal direct product of subgroups H and K, then first H and K have only the identity element in common. What does it mean? It means that the intersection of H with K is nothing but identity element. Second one, G is G is isomorphic to the isomorphic to the external direct product of H by capital A. It means what does it mean? G is isomorphic to H cross K. Okay. Let's see its proof. So first one, we know identity element always belongs to H. Okay. So this implies E is always subset of H intersection K. Now let X belongs to H intersection A. Then X belongs to H and X belongs to K. So this will imply X inverse belongs to H and X inverse belongs to K. Okay. Because H and K are groups. Okay. Since so now I will say let G belongs to G. Then by definition of internal direct product, there exists unique H belongs to H and small k belongs to K, such that G is equal to HK. But G is equal to HK is also can be written as H X, okay, and X inverse K, where HX belongs to H because H belongs to H and X belongs to H. And X inverse K belongs to capital K because X inverse belongs to K and small k belongs to. So, but now by uniqueness of representation, we have what we have, representation is unique. We have what we have because both HK is equal to HX by uniqueness of representation. So this will be H equal to H and this will be equal to this. So this implies H is equal to HX. Okay, and K equal to X inverse K. So you can take this part. You can take this part or you can take this part. Both will conclude that X is going to be identity element. So I am taking this one. So what will happen? I will operate both the sides. So now I can write like that. What is this? this is equal to, I can write by, now by this will be E is equal to F by left cancellation law in G. Okay. So X is going to be identity. It means what? It means what? This implies that if any X belongs to at intersection K, then this implies X is going to be identity. Okay, so what does it mean? It means at intersection K is nothing but contained in E. So from, let's say 2, from 1 and 2. From 1 and 2, we have at intersection K is identity. Okay, so we are done. So first part is true. Now move to second part. We have to show that this is isomorphic at intersection. It is isomorphic to the external direct product of H by K. We are to show. Okay. Now define a map. So given G belongs to G, there exists a unique H belongs to H and K belongs to K, such that G is equal to HK. Okay. So define phi a map from G to H cross K by phi G is equal to H comma K. Okay. So this map is, this phi is well defined by the fact that G is equal to HK is unique representation. Oh. Now we have to show this map is 1, 1 and 1, 2, and it is homomorphic. Okay. So phi is 1, 1. So phi is 1, 1. Let G1 and G2 belongs to G1 and G2 belongs to G, such that phi G1 is equal to phi G2. Okay. Then there exists unique H1 belongs to H and K1 belongs to K, such that G1 is equal to H1 K1 and there exists. So this implies phi G1 is equal to H1 K1, okay? And there exists unique H2 belongs to H and K2 belongs to K, such that G2 is equal to H2 K2. This implies phi G2 is equal to H2 K2. Now phi G1 is equal to phi G2. So this implies H1 K1 is equal to H2 K2. So this implies H1 is equal to H2 and K1 is equal to K2. So this implies G1 is equal to H1, K1 is equal to H2, K2 is equal to G2. So this implies G1 is equal to K2. So this implies phi is 1, 1. Now phi is onto. Second is phi is on. Let Hk belongs to H cross K. Then H belongs to H and K belongs to K. Okay. Put G is equal to HK. This will belong to K and phi Z is equal to HK. Okay. So given H comma K belongs to H cross K, there exists G belongs to G such that phi Z is mapped to HK. Therefore, phi is on. Phi is homomorphic. Now we need to prove that phi is homomorphic. Phi is homomorphic. Not taking. So let G1, G2 belongs to G. Okay. Then there exists unique H1 belongs to H and H2 belongs to K1. K1 belongs to K such that G1 is equal to H1, K1 Okay. Okay. So this implies phi G1 is equal to H1 K1. Okay. Similarly, there exists unit H2 belongs to H and K2 belongs to K, such that G2 is equal to H2 K2. Okay. Now, what is the meaning of this? This implies phi G2 is equal to H2 K2. Okay. Here, I have written wrongly, so I'll correct it here. It should be H1 K1. Okay. Now, what is G1 G2? This is H1 K1 H2 K2. Okay. So I can write it. So I can write it H1 K1 H2 K2. Okay. Now, because every element of K commutes with every element of H, or every element of H commutes with every element of K. So we have what we have? We have K1 H1 H2 is equal to H2 K1. So we will use this fact here to put this value here. H2 K1 K2. So what is this now? H1 H2 K1 K2. And this representation is unique. So, and this representation is unique. Is unique by definition of internal direct product. Okay. So this implies phi G1 G2 is equal to what we have? H1 H2 K1 K2. Now what is this? Okay. Then, so I should type next here. Next. Now, phi G1 G2 is equal to this H1 H2 K1 K2. So this is equal to H1 K1 H2 K2. So what is this? This is nothing but phi J1. And what is this? This is nothing but phi J2. So this implies 5G1 G2 is equal to 5G1 5G2. Okay. So this implies phi is homomorphic. Phi is homomorphic. Since phi is homomorphic, 1, and also we get phi is isomorphism. Phi G2 H cross K is isomorphism on 2. Okay. Hence, G is isomorphic to H cross K. It means symbolically G is isomorphic to H cross K. Okay. So this is proven. Okay. So I would like to write a remark that is very important remark. Okay. If G is an internal direct product of its subgroups H and K, then G is isomorphic to H direct sum external sum by K. Okay. Isomorphic to external direct product of H by K. Okay. H by K. On account of this isomorphism, we shall identify the internal direct product with the external direct product. Okay. If G is the internal direct internal direct product of its subgroups H and K, we shall write G, we shall write G is equal to H direct external direct G is equal to external direct product of H cross K. Okay. So what we have done actually, we are saying that we have proved theorem and we have shown that if G is internal direct product of H and K, then G is isomorphic to external direct product of H by K. So on the account of this isomorphism relation, if G is given as a internal direct product of its subgroups H and K, we will simply write G is equal to H. We will simply write G is equal to external direct product of H by K, because there is a isomorphism relation. Okay. So this is the reason. That is why we are writing like that. Okay. So we have proved this result. Okay. Now we can identify internal direct product as an external direct product. Okay. So thank you very much for today's lecture. If you have any program related to this, you can comment on my YouTube channel. Like, share, comment, and subscribe my YouTube channel. Thank you very much for today's lecture. Thank you very much.